Between the cities of Limoges and Lyon lies a geologic relic, a remnant of a time when the south-central part of what is now France was volcanically active some 10,000 years ago. Known as the Puy de Dôme, the extinct volcano rises to a height of nearly 1,500 meters above sea level, roughly 4,800 feet in imperial units, making it the highest point in the region known as the Massif Central. In prehistoric times, the site served as a spiritual center for the region, and during the period of Roman occupation, there was built there a temple to the god Mercury. Much later, the mountain served as a battleground on several occasions, but not of the sort you might expect. Rather than armies of soldiers fighting for glory on its steep and wooded slopes, the combatants were the riders of the peloton of the Tour de France. First included in the world's greatest sporting spectacle in 1952, the road up the volcano from the valley below stops at the summit, rather than continuing over it and back down, meaning that a given day's stage had to end up at the top of the 14-kilometer climb up that 12% grade. The winner of the stage that first year was Italy's Fausto Coppi, who would go on to win that year's edition of the race. In 1959, Spain's Federico Martin Bahamontes, known as the Eagle of Toledo by his fellow riders, attesting of course to his skill as a climber, would repeat Coppi's feat. In later years, the climb would see other epic days of sporting effort, though none were as fraught as the final day's battle in the 1964 race, where Jacques Anquetil fought off challenger Raymond Poulidor to win his fifth and final Tour de France. In 1975, as he raced to break Anquetil's record of Tour victories, Belgian cyclist Eddy Merckx was punched by a roadside fan, a blow that fractured the cannibal's ribs, injured his kidney, and prevented him from winning a record sixth Tour. The climb would be featured on and off in the Tour, each time offering up a spectacular day of racing, until 1988, when the deterioration of the road surface and then later the construction of a tourist railway made the climb unrideable by a large group of riders. Nevertheless, the mountain has gone down in the annals of bicycle racing as one of its most hallowed locations, and for a time, cyclists would sneak past the barricades placed across the old road to ride the slopes on the single lane that is left, that lane made famous by Bahamontes, Anquetil, Ocana, and Merckx. Today, cyclists are allowed to climb the slopes on Wednesdays and Sundays between 7 and 9 a.m., and so now they may legally experience the suffering the legend of the sports once had to endure to etch their names in its history. What is also true is that few of the 500,000 tourists that ascend to the extinct volcano's summit, either by rail or bicycle, know an even more obscure piece of history. In 1648, through the urging and organization of Blaise Pascal, Florin Perier performed what is thought by many historians of science to be the first truly modern scientific experiment. And as important a milestone as this was, the significance of its occurrence pales in comparison to the larger and more important fundamental change in our understanding of the universe that would ultimately come from it. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 22.1, Supplemental-Puy de Dôme. Evangelista Torricelli had been born on October 15, 1608, in Rome, into a poor family. His father, Gaspare, was a textile worker who had immigrated to the Eternal City from Faenza in the northeastern Italian province of Ravenna. Had it not been for an uncle, he might have never escaped the life on the edge of poverty that was in store for him. However, his parents, seeing that their young son had intellectual gifts beyond those of other children, contacted Gaspare's brother, Jacopo, who was a Camaldolese monk back in Faenza, to see if there was some way the boy could enter into that system of schooling. Jacopo took the young man under his wing to see to his education, going so far as to have him enrolled into a Jesuit college in 1624, when he was just 16 years old. The young man studied mathematics and natural philosophy there for 2 years until his father died, wherein he moved back to Rome to look after his mother and study with Benedetto Castelli, who was the chair of mathematics at the Collegio della Sapienza. While Torricelli did not formally enroll at the university, he served as Castelli's personal secretary for the next 6 years. Castelli was part of a circle of mathematicians who were supporters of Galileo. He'd gotten to know the Florentine mathematician and natural philosopher early in both of their lives, and actually had instructed Galileo's son at one point. When Galileo departed his post as the chair of mathematics at the University of Pisa, he was able to have Castelli appointed in his place. The two men had worked together on problems in hydraulics, and Castelli had assisted Galileo in his observations of sunspots in 1611. Castelli also held an appointment as the abbot of the Benedictine monastery in Monte Cassino, something that brought him to the notice of the Catholic hierarchy, most notably Pope Urban VIII. As part of his work, Castelli had come to learn about a problem that was being discussed by Galileo and another one of his students, one Giovanni Battista Bellini. The two were carrying on a correspondence about the various attempts and failures to pump water up a tube to a height greater than about 32 feet. To get a better sense of this, think of being a miner who is trying to, say, excavate a mine shaft, and you run into a pool of water that is blocking your way. You want to drain the pool of water, and so you drop a pipe from the surface into the pool, and then you attach either a suction pump or a siphon of some sort to the top, a bit like putting a straw in a drink and then sucking at the top of the straw with your mouth to draw the liquid up the straw. What was going on is, if the pipe was less than about 32 feet tall, the pump could pull water up the pipe and then pump it out onto the ground, and you could in time drain that underground pool. But if the height of the pipe was more than 32 feet, the pump would only pull water up to that height and no more. And so the question was, why does this happen, and could it be resolved? Galileo held that if a column of water in a suction pump or in a tube with an airtight seal exceeded 32 feet in its height, the column of water would descend, leaving a vacuum above it due to the weight of the water. He claimed that the water would rise up to that height in order to keep a vacuum from forming. However, he said, above that height, the weight of the water column would sort of break itself, just like a rope dangling from a high enough height would break under its own weight. Bellini, on the other hand, put forward a different idea. He said that suction pumps worked to create a vacuum by first pumping out air. As the air was removed from the tube or the pipe, the weight of the atmosphere on the pool of water would push additional water up the tube until the weight of the water above the original pool was the same as the weight of the atmosphere above the pool minus the weight of the atmosphere above the column of water in the tube. If the suction pump pumped out more air, the water column would rise. However, if there were no air in the pipe, the height of the column would be such that the weight of the water in that column of water would be the same as the weight of all of the atmosphere above the pool that was pushing down on the pool of water. Now, this is a really important conversation on a really important count. It refutes Aristotle's idea that since nature abhorred a vacuum, none could exist. While the two men differed as to why the water rose in a tube or a pipe to a certain height, they both invoked the idea of a naturally occurring vacuum. For Galileo, the water was pulled up the tube as a resistance to the formation of a vacuum, while for Bellini, it was the water being pushed up the evacuated pipe or tube by the pressure, or weight per unit air, of the atmosphere above the tube acting on the pool of water below it. This correspondence between the two men took place in 1630, just 2 years before Galileo's trial before the Inquisition, and, as such, it didn't see the light of day for another 8 years. Not long after this, it seems, René Descartes may have come up with a similar explanation for the phenomenon as Balanini did, and he even suggested in his writing that one might be able to construct an instrument that would be able to measure atmospheric pressure using this idea. He did not, however, follow up on it. Now, I haven't been able to determine whether Castelli knew about the correspondence prior to it reaching Rome in 1638. For most, however, and possibly for Castelli as well, it was the publication of Galileo's two new sciences, something written while the aging mathematician was under house arrest, that was truly the revelation in this matter. Not only did it call into question the basis of the Aristotelian motion ideas that Galileo had been working on early in his career, but it also reworked much of the science of hydraulics, beginning from the work of Archimedes rather than Aristotle. Galileo's claim that a vacuum was being formed at the top of the tube set off a wave of investigation, most notably by Raffaele Maggiotti and Gasparo Berti. The two men took to the investigation by trying to create a better way to sort of figure out the phenomenon, something they did in 1641. What they did was create a long tube with a length greater than 32 feet that was sealed at both ends, but that had a window of sorts for viewing the water level. They would fill the tube while it was laying on the ground and then lift it to a vertical position. One end of the tube was placed into a tub of water, and that end of the tube would be unsealed. What they observed on 4 different iterations of the experiment was that the column of water would descend from the top of the tube until it reached a height of 32 feet. Now, since the space above the water had originally been filled with water, and there was thought to be no way in which air could get into the top of the tube, they concluded that it was possible that the vacuum could have formed. The problem that they saw with this interpretation, though, was that light was able to travel through the empty volume at the top of the tube. When, in a later version of the experiment, they placed a small bell in the empty space, they could still hear it ring, though they couldn't rule out the fact or the possibility that the sound was being transmitted through the mechanism that had been used to attach the bell in place. Unable to either prove or disprove the vacuum hypothesis, the two men moved on to other things. However, while they were working on this, Torricelli came into contact with Galileo. We don't really know what Torricelli did in the years between 1632 and 1641, but one has to think he was active in the mathematical and philosophical communities of Rome. In 1632, he had written to Galileo shortly after the publication of the Dialogue Concerning Two Chief Worldviews, stating his support of Copernicanism. But after Galileo's conviction of heresy came down in early 1633, he, like so many others in Italy and across Catholic parts of Europe, kept any such thoughts to himself, lest he suffer the same fate. Sometime during those intervening 9 years, though, Torricelli took up the study of projectile motion, and in time wrote a monograph on the topic that incorporated Galileo's work. Castelli sent this monograph to Galileo, who then invited Torricelli to come up to the villa he was confined to. Torricelli, after attending to the affairs of his mother's estate following her death in 1640, met with Galileo and stayed with him until his death 3 months later in 1642. Torricelli was then appointed to fill Galileo's roles as chief mathematician to the Grand Duke of Florence and professor of mathematics at the University of Pisa. It would be during this time that he would make some of his greatest contributions to both mathematics and physics. In 1643, he took up the experimental trail that Maggiotti and Berti had abandoned. At first, he used water tubes, just as they did, but soon the people of his neighborhood began to suspect that he was involved in some sort of sorcery or witchcraft. As we've discussed previously, this could have escalated into a very serious charge with even more serious consequences, and so Torricelli sought to devise another way to study the phenomenon. He soon hit upon an idea. He realized that if Balanini's idea for what was going on in the tubes was correct, if the weight of the atmosphere was pushing the water up the tube as it was being evacuated, then it wouldn't matter what the fluid was that he used. What he figured out was that if he were to construct a tube and fill it with mercury, which was about 12 or 13 times denser than water. He would only need a tube that was about 2.5 feet tall instead of one of more than 32 feet in length. Thus, in the privacy of his own home, and away from the prying eyes of his suspicious neighbors, he built the first Mercury barometer. Of course, it wasn't called that at the time, as the name wouldn't be given to the apparatus until around 1665 or 1666, but it functioned in the exact same way such an instrument might today. Shortly after creating this, he wrote to his colleague, Michelangelo Ricci, quote, "Many have said that a vacuum does not exist. Others that it does exist in spite of the repugnance of nature and with difficulty. I know of no one who says that it exists without difficulty and without a resistance from nature. I argue thus: if there can be found a manifest cause from which the resistance can be derived, which is felt if we try to make a vacuum, it seems to me foolish to try to attribute to vacuum those operations which follow evidently from some other cause. And so, by making some very easy calculations, I found that the cause assigned by me, that is, the weight of the atmosphere, ought by itself alone to offer a greater resistance than it does when we try to produce a vacuum." End quote. What, in essence, Torricelli and before him Maggiodi and Berti had done was create a balance that allowed him to weigh the air above him. In his writing to Ricci, he observed, quote, that we live in an ocean of air, end quote, and thus he hypothesized that the weight of the part of the ocean, of air that is, over the apparatus might change depending on climatic conditions. He was able to observe the rising and falling of the column of mercury in the tube, but due to inexperience in setting up the apparatus, his results were inconsistent and difficult to interpret. I should mention here, this is how we arrive at our measurement of barometric pressure. We actually are measuring the height of a mercury column, or at least its equivalent electronically or in some other way nowadays. When we say that the barometric pressure is 30.1, what we really mean is it's 30.1 inches of mercury up in that tube. Unfortunately, before he could really begin to standardize his procedures, something that was beginning to take place in other parts of Europe, he died at the frustratingly young age of 39 in 1647, just a year before his ideas would be shown to be correct in France. In France, a priest by the name of Marin Marsin received a garbled and confusing account of Torricelli's work in 1644. Marsin is a vital figure in science during this time, as he cultivated an extensive network of correspondence throughout the continent and even in England, and as such, he served as a sort of information clearinghouse. Through his network, he created an informal scientific society that would in time become the core of several of the scientific societies that would form in the late 1650s and early 1660s. Marsin attempted to replicate Torricelli's results, but was unable to do so due to the inability to create or procure the right kind of glass tube. As a result, he traveled to Florence in 1644 to meet with Torricelli and to see experiments being done with an eye to being more successful. Unfortunately, upon returning to France, he found that the glass-making industry there was not yet up to the task. Nevertheless, he did continue his correspondence and communicated what he had learned to a bunch of other people. 2 years later, in the autumn of 1646, 2 French investigators were able to finally successfully replicate Torricelli's results. One was a man by the name of Perier, and the other was Blaise Pascal. In both cases, the men used the long tube water method, though Pascal substituted red wine for water, both for ease of measuring the fluid level and to test a hypothesis of the Aristotelians. Wine was thought to be more spirituous, as it were, meaning that it gave off more vapors than water. Therefore, those natural philosophers who clung to the Aristotelian view, which held that the column of fluid in the apparatus was being impeded by filling the full length of the tube due to the presence of vapors in the uppermost part of that column, and that those vapors, sort of pushed the column of water down, said that a column of wine would be pushed to an even lower height than the column of water due to a greater amount of vapor in the upper part of the tube. When Pascal performed the experiment, he found no such effect, thus demonstrating the falsity of the Aristotelian argument. As we will discuss later, this is a really important moment in the history of science. Pascal has performed an experiment to test a hypothesis. Well, this is certainly not the first time such a thing has taken place. His publication of the results and Marsane's subsequent promotion of that publication through his network of correspondence indicates a distinct shift in seeing experiment as being foundationally evidentiary in the establishment of both facts and claims. This was helped along by Pascal's demonstration of the phenomenon as something of a public show. Now, what needs to be understood here is that while Torricelli's experiment had been replicated, his theoretical framework hadn't really traveled with it, at least not at first. Thus, what became the focus of research, especially with Pascal, was the establishment of the fact that there was indeed a vacuum created within the space the fluid had left behind when the column descended that whatever distance that it would descend, so that it was only 32 feet tall. To do this, Pascal did 3 extensions of his original work. The first was that he built an apparatus that placed a second barometer inside of a sort of a largish bulb of evacuated space in the first barometer. As the column of the fluid in the first barometer dropped to its typical height, the height of the column of fluid in the second barometer would drop to nearly 0. This result was consistent with the hypothesis that a vacuum, or at least a strong partial vacuum, was formed in the upper space of the first barometer, as there would be no gas pressure to push up the fluid column in the second barometer left in that space. Several variations of this would be developed by Pascal and others, and it would become an important way of testing the establishment of vacuum conditions. His second test, though, was a stroke of genius that would be hailed by the next generation of scientists as the crucial experiment that established not only the model of Torricelli, but that spurred physics to fundamentally reject Aristotle's ideas regarding the nature of the universe. Pascal in his work had finally run across Torricelli's idea that the column of fluid in a barometer was pushed up by the weight of the air pressing down on the pool of liquid the tube had been stood up into. He reasoned that if this were the case, if one went to a higher altitude, there would be less air on the top of the tube, and thus less weight. This, he reasoned, would cause the column to drop somewhat. It's really an ingenious bit of thinking. He wrote about his idea to his brother-in-law, Florin Perier, who suggested a way to test the prediction. He would construct a barometer in the garden of a monastery a short distance above the base of the mountain near him, the Puy de Dôme, and measure the height of the Mercury column. He and some colleagues would then climb to the summit of the mountain and construct a second barometer there and take a measurement of the height of the column. On September 19th of 1648, Perier, accompanied by a host of local dignitaries, climbed the Puy de Dôme after leaving their first barometer behind in the garden of the monastery. At the summit, overlooking the wide expanse of the Massif Central, the second barometer was constructed and the height of the Mercury column was measured. The mercury in the tube stood some 3 inches lower than it had in the courtyard of the monastery below, as attested by all that were present. They then proceeded to move back down the mountain, stopping 3 more times to construct the barometer and make measurements there. In each case, the column's height was greater than it had been up at the summit of the mountain, and once they got back to the garden at the base of the mountain, it matched the original barometer reading there. They then traveled to a point that was lower down the slopes a little bit than the monastery's garden was, and found that the column was even taller than it had been. So excited was the group by their results that on the next day they repeated their procedure, but this time they did so between the base of the cathedral church in nearby Clermont and at the top of its tower. While the difference was fairly small, only about 0.2 of an inch, it clearly established the principle. When Perier wrote back to Pascal to inform him of the results, Pascal went out and repeated the cathedral experiment with as many of the tall buildings in Paris as he could find, thus establishing that what was being observed was not a local phenomenon, but rather a consistent physical fact that supported Baleni's and Torricelli's claim that it was atmospheric pressure that pushed the column of fluid up the pipe, and that, if a filled tube was stood up and had some portion of the tube left absent of fluid, that space in there would actually be a vacuum. Now, as a note here, not everyone was convinced of this presence of a vacuum idea that Pascal had. René Descartes, who would, for his entire life, deny the existence of a vacuum, claimed that if light traveled through the space, something that could clearly be seen, there had to be something in that space. He proposed that there was a weightless, invisible ether that still occupied the supposedly evacuated volume. And this is where the third experiment becomes important. Here, a man by the name of Gilles de Roberval placed the bladder of a carp, a fish that is, in the space at the top of the tube. Now, Roberval did everything he could to push all of the air out of the bladder by flattening it and then sealing it up tight before placing it in the tube. When the tube was stood up and the mercury dropped, the bladder ballooned up. Now, there are a couple of interpretations of this observation that would show the need for additional investigation on the nature of the vacuum. Pascal and other vacuum proponents said that Roberval had left a tiny little bit of air in the bladder, and so when the external air pressure had been removed, that air in the bladder had swelled, causing the bladder to expand. Roberval, on the other hand, said that if there were air left in the bladder, then there could also be air left in the top of the tube, and thus a true vacuum didn't actually exist. This second explanation implied that there might be some relationship between the pressure on the gas and the volume that the gas would be able to occupy. What these three experiments would do was create a baseline of accepted tests that anyone studying the phenomenon would have to be able to replicate. This set of test experiments, if one wishes to give them some sort of a name, I'll call them test experiments, were carried out in that period between 1646 to 1648 by a number of researchers, all connected to Mersenne, who collected and disseminated everybody's work. While there were differences among the correspondents on how to interpret the results of various experiments, what was not argued about were the experiments themselves. Everyone was able to replicate them and see the same things over and over again. Any new equipment or apparatus would have to produce results consistent with these tests, or they'd be held in suspicion, and the results would be discounted until they could be sort of put back into place. More than that, though, there was an accumulation of a body of experimental and procedural knowledge that was shared among the group. Everyone benefited from the mistakes and discovered techniques of the others. Things such as, not breathing on the mercury when working with it, as that would introduce water vapor into the sample and the apparatus, and that would thus compromise the results. However, when Mersenne dies in 1648, this network sort of foundered, and there was little additional progress made in France on addressing the vacuum question. However, compilations of the work were eventually gathered and published in various places, including England, Italy, and Poland. One of the men who read these works was Otto Von Gierke, in the German town of Magdeburg. In 1654, Von Gerkey invented a mechanical vacuum pump that he used in a variety of experiments, the most famous of which had to do with his hemispheres. This demonstration involved him constructing two large hemispheres out of metal that, when placed together along the rim at the bottoms, would form a good seal. Von Gierke then used his vacuum pump to remove the air from the space inside of the two joined hemispheres. The now evacuated sphere, since you had two hemispheres that made a full sphere, was attached to two horse teams that would pull in opposite directions. When spurred on, and by the way, this was usually done in front of a large crowd in public with lots of observers, as it was something of a spectacle, the teams were unable to separate the hemispheres. Von Gierke then opened a valve on one of the hemispheres and let air in from the outside into the hemispheres, or at least into that spherical space between the two hemispheres. At that point, when the horse teams pulled, they were easily able to separate the two hemispheres. Von Gierke's interpretation of this demonstration was to say that a vacuum had been established inside the sphere and that the outside air pressure, now no longer balanced by any internal pressure, pushed the two hemispheres together so hard that they could not be separated. This further promoted the idea of the existence of a vacuum, but more importantly, it demonstrated how one might construct a vacuum pump. This would be seized on by an English alchemist and natural philosopher by the name of Robert Boyle, who would use the new pump to conduct a number of experiments that would establish what was meant by a vacuum and develop the first description of the behavior of gases. By the time Boyle succeeds in replicating von Gierke's vacuum pump and begins performing various tests in evacuated glass enclosures using it, he is the beneficiary of one of the most important advances to have taken place in the scientific revolution, that of the scientific community. What had originally been an informal correspondence network through the work of Mersenne would be transformed into what we now call scientific societies. These groups would formalize the functions and values of the group of individual researchers who had worked together through Mersenne to create a common body of practice and knowledge, with the most fundamental requirement being that of reproducibility. In Florence, when the Accademia del Cimento forms, it will adopt the model provando e riprovando from Dante, indicating its belief that the successful reproduction of experimental results is the hallmark of knowledge that can be trusted, i.e., the evidence needed to establish facts we discussed in our last episode. Similarly, when the Royal Society in England and the Académie Royale in France are established, they will require such replication of experimental results. In addition, both of these scientific societies will quickly establish the first journals to disseminate the results of work that had been demonstrated at their meetings. It is this movement towards formal scientific community that is a hallmark of the scientific revolution. Even those historians of science who are skeptical of there actually being a revolution acknowledge that this is a unique moment in European history. With it comes the belief in progress as an inevitable consequence of the work of such communities. It would be Pascal who would write that, quote, "All mankind continually makes progress as the world grows older," end quote. The sentiment would have been foreign to most Europeans just 100 years earlier. Our modern view of progress, that we will know more, see further, have more material prosperity, etc., can be traced back to the work of Torricelli and Pascal as communicated by Mersenne. It will be in this context that Boyle, one of the founders of the Royal Society and a regular demonstrator there, would do his work that would lead in 1662 to the establishment of a natural law now known as Boyle's Law, that related the pressure and volume of a gas. The vacuum pump he used was constructed by the Royal Society's chief demonstrator, one Robert Hooke, whom we will have occasion to speak about in some length in a later episode. It is during this time that what we really think of as science begins to detach itself from what we might call natural philosophy. In 1660, English investigators begin to use the term experimental philosophy to denote the work that is based on carefully controlled and replicatable experiments from that field based on philosophical speculation about the natural world. While it is clear that such practices can be dated back through Galileo, Gilbert, and Brahe, to even Ibn al-Haytham's work in optics, it is at this time that such an approach becomes institutionalized and the knowledge derived at it through the processes and procedures it espouses begins to be held in higher esteem when describing the natural world. This new paradigm of investigation is, as we have said earlier, dependent on and spurred on by the existence of a book culture that rapidly and clearly communicates the results of one's work for relatively quick checking. What is important is that when Boyle begins his investigations with the air pump, he first has to establish its validity as an apparatus by replicating the barometer and fish bladder experiments we discussed earlier, as well as a number of variations on those things. When he shows that his evacuated hollow glass sphere can reproduce the case where the height of the Mercury column of a second barometer placed inside falls close to zero, he is demonstrating that he can create the same conditions inside his sphere that Pascal did inside the space above the column of Mercury in his larger barometer. Boyle is thus able to claim that he has formed a vacuum and can therefore talk about his investigations inside of his sphere as being fully equivalent to something that Pascal might have done, even if the apparatus is different. One example of this is to observe what happens to a flame in a vacuum. This is something you can't do in a mercury barometer. As you know, you can't take that burning object, whether it's a candle or a match or whatever you might say, and pass it through the mercury unaffected. However, a lit candle can be placed in the sphere that would then be sealed and have the air removed from it by a pump. While these experiments didn't address the arguments of those who claimed an ether was necessary to transmit light, they did reinforce that such an argument was sort of grasping at straws, sort of a post hoc kind of thing. It wouldn't be actually until Newton's proposal of an action at a distance force that could reach across empty space that the idea that light could travel without a medium would become more acceptable. Though it should be noted that it wouldn't be until Albert Einstein's special theory of relativity in 1905 that this idea of an ether would finally be put to rest. As we look back upon that moment in time, the significance of the Puy de Dôme event becomes much clearer. It represents all of the things we have discussed regarding the scientific revolution. The crowd of dignitaries gathered not out of some scientific interest, but rather because they thought they were about to discover something new. The proposal of the experiment and the transmission of its results happened because of the formation of a scientific network. That scientific network placed as its highest value the reproducibility of results of experiments and observations. Those results were communicated through the publication of books and journals, supported and promoted by the very communities of investigators who were participating in the work being done. In this way, investigation took place in a fully open society where all interested parties could check each other's work. Moreover, though, the experiment was important because it shattered the beliefs of the natural philosophers in the scholastic universities in Europe. It established among those who followed a mechanical, atomistic view of nature that there could be a place without matter, i.e., a vacuum. These individuals included both Boyle and Newton, who called the experiment the quote-unquote experimentum crucis, the crucial experiment. Now, as I bring this episode to a close, I want to apologize for its relative brevity. This last week was final exams for me, so most of my research and writing time has gone into grading papers and exams. As is always the case, some of my students did well and some didn't, but it was a privilege to be part of their process of learning, and I'm thankful for that. Hopefully, going forward in the next couple of weeks, I'll be able to put a bit more time into the show, maybe even get ahead some. It'll be nice to be able to read and think without having the pressure of having to grade a stack of homework or write a new curriculum for a little while. By the way, if you'd like to know more about what we're up to and haven't already done so, consider liking our Facebook page. We post a lot of stuff there. Different kinds of articles, things that I find that are going on in the research community, stuff that relates to what we're talking about in the podcasts. If that's something you might be interested in, head on over and take a look. Also, do subscribe to the show so that you can receive our latest episodes without having to work about trying to track them down. And finally, if you're so inclined, leave us a review on whatever service you use to listen to us on. Also, I'd like to say thanks to the folks over at the Blue Dot Sessions, this musical collaborative that provides the music that we use in our show. If you're enjoying that sort of thing, that great instrumental ambiance, I suggest you head over to their website, www.sessions.blue, and give them a listen. They're absolutely fantastic. Next week, we'll wrap up this portion of our narrative before setting out to new vistas. And we'll do that by looking at the trial of Galileo and its effects on scientific thought throughout Europe. Until then, full sails on your journey.